Okay, now you're asked to graph a couple of functions. So let's start with the first one. Now, to graph any function, we start by asking two questions. What are the x-intercepts? What are the y-intercepts? We want to write this out to remind ourselves. It's kind of an automatic thing. X-intercepts, y equals 0. And if y equals 0, that tells us that y here is 0, so all this is equal to 0. Now, you can shortcut this and see immediately what the zeros are, but I recommend again that you write it out same way every time. You write out x minus 3 equals 0, or x plus 5 equals 0, or x minus 8 equals 0. Because this reminds you the logic of what you're doing. And then you can solve these equations. So no matter what you have in parentheses here, you can write it as an equation equal to 0. Each factor in parentheses would be set equal to 0, and you would solve. So this prepares you for that possibility. Okay, so we get x equals 3, or x equals negative 5, or x equals 8. So the x-intercepts are 3, 0, negative 5, 0, and 8, 0. Some of you copied this 3 down as a 5, and that's no problem. Then you have 5, 0 instead of 3, 0. Well, we can put all this on the graph. So immediately we can sketch our graph. And so x equals negative 5 is here. Then x equals 8 will be out maybe about here. And x equals 3, maybe about here. And then we find the y-intercept. And we remind ourselves that x equals 0. So we get y equals 0 minus 3 times 0 plus 5 times 0 minus 8. And that multiplies out to 120. So we put our y-intercept up here. On the y-axis, where x equals 0, we're going to have the point where y equals 120. Now we can mark our x-intercepts. And normally I label these. Graph is a little small. It has any label, but I guess I'm going to. Okay. We have negative 5, 0 here. We're going to have 3, 0 here. And we're going to have 8, 0 here. And of course, the y-intercept is at 0, 120. Okay, well, we now long run behavior, and we want to write this out. Leading term is x cubed. Because clearly, if I expand this, if I expand these two, I'm going to get an x squared, and then I'm going to have an x to multiply that x squared. It's going to give me an x cubed. So the highest power term will be x cubed. So I say the long run looks like this. If we zoom way back on this function, it's going to be just like a cubic function. Then we remind ourselves that we can have wiggles in here. And these are our wiggles, or at least what we're going to get in a minute. So this tells us that as we move away from the wiggles on the left, we're going to go down. As we move away from the wiggles on the right, we're going to go up. So that the long run behavior is going to be like so. It's going to be down here, it's going to be up here. And now we can sketch a reasonable graph that follows that behavior. And everybody got a graph that looked, I think, much like that. And I realize that I'm just a little bit off of the screen here. So let's make sure we see everything we've done. We've got all three of our zeros with the x equals -5, x equals 3, x equals 8 lines labeled. The y equals 120 line labeled, and the x-intercepts marked and the y-intercept marked and labeled. Then we mention our long run behavior is going to look like this. Okay. That's the foundational process. Now there's more to it, but in this class, we're going to just make sure we understand this much so that when we encounter it in pre-calculus, we can go a little bit further with it. Okay. Now, the other question is this rational function. Not sure that was a fair question to ask for a quiz, but I'm going to say that some people did some work on that part. Okay, so this is a rational function. Which means it's a polynomial divided by a polynomial. Okay. Now we expect if the polynomials in lowest terms, and that's the case that we'll talk about now, then we have zeros where the numerator is 0 and vertical asymptotes where the denominator is 0. So first thing we look at is x-intercept. That occurs for y equals 0. So we have x minus 3 over x plus 4 equals 0. Now, the only way this could be 0 is for the numerator to be 0. Because no matter what the denominator is, if the numerator isn't 0, we're not getting 0. Okay? So the x equals 3, and the x-intercept is going to be at the point 3, 0. This means we can begin sketching our graph. Okay, so we go ahead and sketch a line, vertical line, for x equals 3, and we put a mark here. That's going to be the x-intercept. And the y-intercept occurs when x equals 0. We get y equals 0 minus 3 over 0 plus 4, which is negative 3/4. So we can sketch a line below the x-axis and call that y equals negative 3/4. And here's our y-intercept. Now we get to vertical asymptotes. Maybe just a single asymptote, maybe it's multiple asymptotes. This occurs where the denominator equals 0. Well, the denominator is x plus 4. So we write x plus 4 equals 0. We solve that, we get x equals negative 4. So we put x equals 4 here, and we know that there's a vertical asymptote here. Now, we're not quite sure what to do, maybe about that vertical asymptote. So we want to look a little bit more closely. Redraw the graph. I'm going to need a little more room. I better redraw this thing. A little bit of room to the left. We're just gonna note for now that this is a vertical asymptote. It's gonna turn out that the graph of this function is going to act like the reciprocal graph around the vertical asymptote. I'm just going to kind of sketch. Remember what the reciprocal graph looks like. It looks like this. Okay. Okay, so we want to look at the long run behavior before we put too much of the vertical asymptote. Okay, the absolute value of x is very large. These aren't very different. Like if x is 1,000,000, then this would be 999,997, and this would be 1,000,004. Just a little bit less than 1,000,000, a little bit more than 1,000,000, meaning that these two are practically the same size. So the absolute value of x minus 3 over absolute value of x plus 4 is going to be close to 1. Now there's a rule for determining this that we'll see in a little bit more detail when we look at another example or two. But what this is going to mean is that up here at y equals 1, write this. Okay. Y is going to be close to 1. So the long run behavior looks something like this. Here we have x equals -4. We're going to have a function that looks something like this. I haven't given myself room to really draw it very well. Something like this. And maybe I better redraw that just a little bit more clearly. What it's going to do is actually something very much like this. So you can see that we have this behavior like the reciprocal function. Except that we have like a negative multiple of the reciprocal function, which would flip the graph over the x-axis, so it would look more like this. So anyhow, there are rules for doing this. It turns out that the graph of this function will go through this point to this point. It's going to be asymptotic to the y equals 1. So maybe looking something like this. And on this side, it's going to look like so. Okay, I'm going to do another example to show you how these things can be constructed without a whole lot of discussion or why they behave the way they do. I'm going to consider this function. Here's something you can take as a rule. The x-intercept, of course, occurs for y equals 0. And the only way the value of the function can be 0, the only way this expression can be 0 is for the numerator be 0. So when you start working these, that's maybe the first thing you want to write down. Then y-intercept occurs when x equals 0, so you work that out. And then vertical asymptote or asymptotes occur when the denominator is 0. So I'm going to ask you to go ahead and see if you can fill in what you get. Okay, what are your x-intercepts? Numerator 0. What values give you the numerator equals 0? Y-intercept, where x equals 0. You can evaluate that. And then vertical asymptotes occur where the denominator is 0. So go ahead and work on that just a little bit. I'll give you a minute to get started, and then I'll start looking over your shoulder and give you some pointers if you need them. Okay, now we're doing quite well with this. Okay, so let's just see how this works out. And we'll start Well, seeing where the x-intercepts are, they occur when y equals 0. So that the denominator doesn't affect whether y equals 0 or not. The numerator has to be 0 in order to make the fraction 0. So that we set x minus 3 times x plus 8 equals 0, which gives us x minus 3 equals 0, or x plus 8 equals 0. So that x equals 3, or x equals negative 8. So the x-intercepts end up being at 3, 0, and at negative 8, 0. Get the y-intercepts. Y-intercepts occur when x equals 0. So we get y equals 0 minus 3. And let me write that out just a little more in detail, and let me kind of recommend that you write it out similarly. Y equals r of 0 equals 0 minus 3 times 0 plus 8 over 0 plus 2. That equals negative 24 over 2, which is negative 12. So your y-intercept is at 0, negative 12. Then you get your vertical asymptotes, which occur when the denominator is 0. Okay, so you get x plus 2 equals 0. You get x equals negative 2. Okay, so we can begin to get the graph. We'll put x equals negative 8 here. And since we have an x-intercept at negative 8, 0, we'll go ahead and indicate that 0. There, that x-intercept. And x-intercept at 3, 0, so we'll put an x-intercept here. We have a vertical asymptote. Sorry, let's do the y-intercept. The y-intercept is at 0, negative 12. So we'll go ahead and arbitrarily put y equals negative 12 here. So this gives us 3 points on the graph. Now the asymptote doesn't give us a point. Let's just see what the asymptote does. X equals negative 2 would be about there. My scale isn't great, but there it is. Okay. And now the graph is going to approach x equals negative 2, much like the way a reciprocal function or reciprocal square function approaches the y-axis. Okay, so vertical asymptotes. Let me just draw. A vertical asymptote could be like this. It could be like this. It could be like this. Well, it could be like this. Those are four basic shapes of vertical asymptotes. And the vertical line, the y-axis in each of these graphs corresponds to this vertical line. Now, there are rules for the asymptotes, but I'm going to kind of gloss around that for a minute. And before, so we can do a couple more examples. I think maybe we don't see the whole board here. That's the camera. Okay, so there's a little more to how this graph appears. The other thing is the long run behavior. And it's going to turn out, without getting into the rule yet for the long run behavior, the long run behavior is going to pretty much be like this. Pretty much like a straight line with withers in the middle. So I'll kind of indicate that here. A straight line, your wiggles can include asymptotes. Okay, well, what then has to happen is I'm going to draw this without a lot of explanation, okay? We'll fill in more details of explanation as we go. The graph is going to start down here, and it's going to come up through this point, and then it's going to approach a vertical asymptote like so. Then it's going to flip down here, and it's going to come through here, and it's going to go off like this. Okay, so the one thing I want you to see at this point is, do we have a vertical asymptote here? It behaves like this. Can you see that this is the way the function behaves with this asymptote? I want you to see that. We'll get a little more explanation as we go. So I think what I'm going to do is I'm going to make my vertical asymptote perfect. Okay, and I'm going to make all these vertical asymptotes purple here, just to invoke the idea of the way vertical asymptote looks. This allows you to fit all the points without going through the x-axis at any point where you're not allowed to, going through the y-axis where you have to, going through the x-axis where you have to, and approaching the asymptote. Okay, now I'm going to give you a couple of more general rules. Now, I don't want to take an example. Might be a little more useful to you. Let me go ahead and adjust my camera slightly. Okay. Let's look at this function. We see. Now, I want you to write this out completely. Don't shortcut it like I'm doing here. But I'm just giving you a summary of what you would get if you did what you've done all along. Your x-intercepts are going to be at 3, 0, 7, 0, negative 5, 0. Your y-intercept will be when x equals 0, you're going to get negative 15, you're going to get 105 divided by 2, which is going to be 50. It's 0.52 and a half. The vertical asymptote Yeah, 0. I wasn't thinking. And x equals -2. Okay, so all that you all should be in good shape with, okay? Now let's look a little more at the way this function behaves. Okay, so we're going to expand this function. No, we could expand the denominator also, but we're just going to expand the numerator because the denominator is already expanded. And I think we're going to end up with x cubed. Now I'm going to do this in my head, and it'll probably be wrong. And then we're going to have, let's say, -2x. We're going to have a 2x squared. And then we're going to have 3x squared. So I think we have a -5x squared. And then on x, we're going to have -35x. And we're going to have -3 times -2, 6x. I remember my signs right, it's -29x. And then it's going to be plus 105. Okay. I think I expanded that correctly. I didn't want to go through the detail of writing it out. If I'm wrong, it's easy to be corrected. You still get the idea. Okay, that's over x plus 2. Okay. Now, I do a long division. X plus 2 into x cubed minus 5x squared minus 29x plus 105. That'll give me x squared, which will give me an x cubed plus 2x. Remember to subtract, I get an x squared. I get a -7x squared. I'll put my -29x down there. So I'm going to get -7x. It'll give me -7x squared minus 14x. And that's going to give me -15x plus 105. So that's going to be plus 15. I don't know where I'm getting plus 15. It's minus 15. Minus 15x minus 30, leaving me a remainder of 135. If I've done this correctly, then my final division will be x squared minus 7x plus 15 plus the remainder over x plus 2. That's 135 over x plus 2. So now I can write y equals, I'll write this out, x cubed minus 5x squared minus 29x plus 105 divided by x plus 2, and that equals x squared minus 7x minus 15 plus 105 over x plus 2. Now, the reason I've done that, and it's not something I'll always have you do, but I could have you do it. When I graph this thing, its long run behavior is this function plus this function. Okay, well, what does the graph of x squared minus 7x minus 15 look like? Well, it's got an x-intercept at 7/2. That would be if x equals 3.5. That's the axis of symmetry with this quadratic function. If I plug in 7/2 for x, I find that the y-intercept is at, okay, let's see. I shouldn't put myself in a position having to do all this arithmetic. So without figuring out the exact coordinates of the vertex, because we don't really need it, but the vertex is at approximately 7/2, and I'm thinking it's negative 30 something, but I'll say about negative 40. And we're going to have zeros. We could figure out the zeros, but we could figure out the y-intercept, which would be at negative 15. And that would be good enough. And now we can get a fairly good picture of the graph of x squared plus 7x minus 15. Okay, now again, we're not ordinarily going to do that, but I do that to convince you that, well, the other function is 105 over x plus 2. Now that's just a vertically stretched 1 over x plus 2 function. It's a vertically stretched reciprocal function shifted over 2 units, shifted to the left 2 units. And this is going to be a reciprocal function with an asymptote at x equals negative 2. Just look at this. This is 1 over x plus 2, which is just like 1 over x shifted 2 units to the left, and then vertically stretched by factor 105. So it's stretched way the heck out. But right here, we've got this y is 105 over x plus 2 function. That's added to this parabola so that the whole point here is when x gets big to the right, we're going to follow this parabola. So we're going to go up like so. When x gets big to the left, we're going to follow this parabola. So it's going to go up like so. In between, we got wiggles and zeros, which are going to give us this asymptote and everything else. Okay, so by the long division, this function is the sum of this parabola that does this and this vertically stretched and horizontally shifted reciprocal function, which looks like this. You put those two together, and what do you have? come back to what we've got here. Our x-intercepts are 3070, -50. Here. Um, here. And x equals -5 would be about, maybe there. Y-intercept is 0.52½. That puts you here. And then the vertical asymptote at x equals -2. The long run behavior, when we divided the denominator into the numerator, we got a quadratic function, which goes up when you go to the right, goes up when you go to the left. So our long run behavior is up here, and it's up here. Now we've got to go through these points if something doesn't work here. Okay, there's something amiss here. I'm not seeing a way to get started over here because I didn't mark my 0 at this point. So I wasn't thinking all that clearly. I didn't mark everything. Okay, so now what we get is our asymptote's going to look like this. Okay. But to the far left, we got to be way up. So we come down from way up here. And we go through this asymptote and then we approach. We go through the 0 and then we approach our vertical asymptote here. So this behaves the way it's supposed to. And then it comes down from our vertical asymptote through the y-axis here. And it continues on down, so it can go through 0 here. Then it turns around and takes off back up. So it looks like this. And that's the graph of our function. Not sure we're totally in focus. Okay, well, for this example, the degree of the numerator is 3. The degree of the denominator is 1. Not a 2, but. And it's x plus 2, not x minus 2, okay. The numerator is 3, degree of the denominator is 1. So this x large magnitude of x. For x values, way to the right, big positive numbers, x values way to the left, big negative numbers. We can say give it its name here, R of x, so I can talk about it. For large absolute value of x, R of x acts sort of like x cubed over x. Because we have an x cubed in the numerator, we just have an x in the denominator. Or x squared. Now, when we did the long division, we got a quadratic function, which is just basically an x squared function, but it's been shifted, stretched. Okay, this one hasn't been stretched. Okay. Whether x is a large positive or a large negative number, x squared is a large positive number. So the long run behavior is like this. We go out to large positive x, the thing goes up. We go to large negative x, it goes up. So we see it goes up here, it goes up here. And it all comes down to the degree of the numerator and the degree of the denominator. Okay, there's more to it. You'll see some of it in your assignment. But I think you're going to be pretty well prepared when we get to it in pre-calculus.